Thanks, Ryan. Thanks for the invitation. It's a great pleasure and a great honor to be online to talk to many of you who are experts on manifold games. So today I'm going to talk about manifold type games, which is a kind of variation of the idea of the dependence of the cost functions on the distribution of agents or distribution of states of individual agents. So we have been doing that the last 5 to 6 years now, and it's different from manifold games from the perspective of symmetry, from the perspective of nonlinearity, and multiple other properties I will highlight in this presentation. So the work is a collaboration from several people from several groups, some in France, some from the US, some from Asia, and some from my own research group. In particular, Julian Barrero Gomez is my postdoc, Sarah Shukri, another postdoc, and then my PhD students and previous postdocs who are still as a collaborator. I would like to thank the US Air Force who is supporting us for the grants on manifold type games, in particular the foundation of it, which would allow us to do somehow more advanced study on this stuff. All right, so first I will somehow introduce the basic problem that start deviating from manifold games, and then introduce variance-aware control problems and rate-sensitive problems. And then progressively, I will move to manifold type game problem. And the last part, which is the main focus here, will be on COVID-19 and how we can use the theory to model and understand the spread of COVID-19 and some of the consequences, in particular, economic consequences and the risk shared or the propagation of the risk in other areas. All right, so I don't need to recall now what is manifold games. I guess this slide is probably less useful now, but for those who are beginners and who are joining us for the first time, still you might grab some references there and enrich your literature. One thing I want to mention here is that the manifold games, as we understand or as we explain now, is different from classical game theory in terms of optimality equation. And the optimality equation brings a Bellman equation together with a Fokker-Planck equation. If you take this as the key property, then it was there. And this goes back to Jovanovic in the 80s. You will find in this paper, Bellman equation coupled with Kolmogorov equation. So I mentioned those references in the discrete time manifold game case. Now for continuous time, it's relatively new in the sense that the Bellman in continuous time brings the Hamilton-Jacobi Bellman equation, and that's quite more recent than the discrete time equations. But since we are discretizing the same equations and we are coming back to the discrete time, discrete state, then we are really in the setup developed by Jovanovic and Rosenthal. That's in this second group of papers that are mentioned here. And they also introduce common noise in the third reference here. Common noise in the sense that the manifold limit, the distribution itself is a random measure. That's already appears in the 92 paper here, for example. So some of you might be interested in grabbing those things, and maybe there are some connections to application to economics and other fields as well. All right, so the idea of rate-sensitive manifold games starts with this functional, which is the exponentiated long-term cost. You take a long-term cost, that is CI. Gamma is the rate-sensitive index of agent I. We have here a finite number of agents. So you exponentiate the cost and then take the expected value of it and then take the log of it. 1 over gamma is a normalization. Now, when gamma is positive, you are taking a risk. You are risk-seeking. When it's negative, you are risk-averse. When it goes to 0, you are risk-neutral. And when gamma is small, actually, you can see that there is, by Taylor expansion here, second order term would be the variance of CI. So you look at not only the first order, but also the second order and higher orders, because the exponential involve all the moments, right? So you get higher order terms of the cost function. Now, why is this interesting? Well, it is interesting because the Nash equilibria, the optimal strategy of under this new performance is, as gamma goes to zero, you might connect to the classical risk network cases. And when gamma is not zero, actually you might have different behavior. So it's very interesting to mix some players. Some players might be risk-seeking, some others are risk-averse, some others are neutral. So all those type of players are part of the game, and we should model them together, not just risk-seeking players, not just risk-neutral players, because we have different sensitivity toward the risk. And that was the idea. And we have, together with Konyon Zhu and Professor Bashar, we introduced the risk sensitivity in the context of meaningful games that goes back to 2014 and 2011 for the discrete state case. And before risk sensitive cases were analyzed, in the context of stochastic differential games, and earlier work goes back to the 70s. So the extension was done for meaningful games here, and then other extension to discrete time and the linear quadratic case and meaningful type control case by Professor Geish and myself. So what is meaningful type control? Meaningful type control is a control of Markin-Vlasov equations, Markin-Vlasov systems. So it means that you have a dynamics that involve the distribution, and the cost function involve also the distribution. What is different from basic means that the agent here, the controller here, influences the entire mass. So you can control the entire mass. Well, in meaningful games, you cannot control the entire mass because you are too small, right? A simple agent is too small to control the mass in meaningful games, although in meaningful type control, a single agent can control the entire mass. So that makes a difference, because the distribution is dependent on the control of the individual. And so you get different optimality equations when you do calculus of variation or on meaningful type control was introduced by Professor Geish and his co-authors, Anderson and Geish, here in 2011. And previously, they have studied the Markin-Vlasov convergence of the Markin-Vlasov equation in 2009. Now, what they have done was function of the moment, so people extended to include the entire distribution later on in the subsequent references or so. So this is a huge, literature, and it's somehow giving social costs. When you optimize social cost in meaningful games, you start moving to this direction. That's the connection with meaningful games to meaningful control. Now, we started from here for meaningful type control and extended to more than one agent, means more than one controller. So that's when the controllers are optimized. So the meaningful type game is here, and so this is for more than two controllers. Now, when you look at the problem, you realize that actually there are some connections between classical game theory and meaningful type game theory, because you can get the classical game theory by just removing the distribution in the cost function. So this first group of references is about meaningful type control and their control of Markin-Vlasov. And then the second group of papers you see here are about meaningful type games. And so different methods have been developed. First group is about maximum principle, Pontryagin maximum principle, calculus of variations. Second group is about dynamic programming, Bellman equations, Bellman principles. And the third group is about direct method. It means you do calculus of variation, but you add a verification method on it, and then you do identification. So it's direct in the sense that there is no PDE to solve. You just check the optimality directly. And then other group of method that we tried that we use polynomial chaos expansion, linear chaos expansion, and so on. So there are a bunch of techniques that have been developed to solve this. But actually, when you do the numerics, you actually need another step in those methods, in at least many of them. So let me briefly explain our main motivation to use this theory for in the context of engineering, because many engineering systems are somehow involve some uncertainties, so they are stochastic. For example, in power systems, we had a couple of presentations applying power systems here. In power systems, demand right now demand is a huge problem in many countries. We are getting outage. We are getting some blackout in some part of the world. So power systems, and we want to reduce the risk of getting, for example, disconnected. And then traffic systems and transportation systems, we have uncertainty about demand, number of vehicles, uncertainty about the incidence over the road. We do have uncertainty in social networks on the number of followers, on the noise, on the fake news, and so on, how it propagates, and uncertainty in blockchains with application to cryptocurrencies, the variance of some of the cryptocurrencies, for example, Bitcoin is completely crazy high variance there. So you wonder how to reduce the variance, and when you reduce the variance in this context, it becomes stable coins. So from classical Bitcoins, you move to stable coins also, and other applications in water networks, drinking water, eating systems. So what I want to highlight here is that actually, if you have a problem in your power systems, it's affect the traffic system because you are consuming energy. It's affect the social networks because your internet is up. It's affect the blockchains because you are running servers that use the power stuff, and it's affect the water system because the water is using, for example, energy for heating the water, for example. So all these systems are actually interconnected and related. So you cannot study one of them by forgetting what is happening in the other systems. This is what we call systems of systems or interdependent systems. So if you think that you can use meaningful games to model power systems and use meaningful games to model traffic systems, then you will realize that actually the traffic system is correlated to the power system, because if the power goes off, the traffic will be affected somehow. So that's the type of thing we want to model. So multi-systems, you can zoom in and you get another game, and you get it games in games. Now, the idea is that if you have a risk in one of those systems, how does it propagate and affect into the other systems? And for that, I would need to start with a basic example and to see how the variance, for example, propagate in other systems. All right, so I don't need this slide. I already explained the connection. So each system will be modeled through a graph, because then it will be much easier to understand the propagation over a graph, because we can use discrete optimization over there, and then numerically this makes simpler. Because if we go to the PDE, we will discretize the PDE. And when we discretize the PDE, we are back somehow to this type of graph indirectly, right? So that's why we start from here, and then everything will be discrete. Time will be discretized, state will be discretized into those type of graphs. Now you'll see the connections between the graph, which explain the interdependence between the different systems or networks. All right. So let's start with the basic variance optimization problem. So this goes back to Markovich, who got the Nobel Prize in 1990. And the idea was to diversify your portfolio. For example, if you have ACE1 and 2, they have different variance, different standard deviation, sigma 1 and sigma 2, but sigma 2 is higher than sigma 1. So sigma 2 is higher than sigma 1. That means that the S2 is riskier than 1. You have more risk in 2 than 1. Though they might give the same return in expected value. So if you optimize the expected value, you are getting R in both sides, it doesn't make any difference for you. But actually, it makes a difference because if you take a risk, you might get sometime higher return, but of course you might lose also. So that's the idea of considering the risk into the system. So he proposed to look at mean variance optimization. So mean minus variance was considered here. And in economics, they have considered a two-stage case, and then people have extended to multiple portfolios and multiple steps. So this is our main motivation actually to study, variance-aware control problems, because when you put a control in it, then the variance of the states will appear in the control problem, and the variance of the control as well sometimes. Therefore, the problem will be somehow different because the variance is nonlinear in the measure, right? So variance is nonlinear in the measure. Now, I apply this to temperature control. So here is a system, and you do a controller that's, for example, input says heating or cooling system, and you make it continuous set from 0 to 1 or from -1 to +1, so that is convex and temperature. Scenario 1 is expected value, the risk neutral, and scenario 2 is the risk aware one. And you could see that the second scenario, the variance is much smaller than the first one, although there is some bigger oscillation in the beginning, but smaller variances for the second one. So that's the advantage of doing a risk-aware control. In risk-aware control or in variance-aware control, the variance is smaller than the classical risk-neutral control. All right. So can we formulate the previous problem? So the idea is the second moment, and this is the mean square. So mean state square at time t1. We are optimizing from t0 to t1. This is the kinetic energy. So this is the control action. You multiply by the density. You multiply by the measure, the distribution of S is mu, and this is the mean square. So somehow similar to the terminal one. And you want to find A and minimize this loss functional subject to the dynamics that is here. So this is the basic Fokker-Planck equation where the velocity is A, right? So the drift is given by A. And there is a Laplacian I add here. Sometimes I put some epsilon, sometimes not. So this is in R, but it could be also 2D. I mean, any Euclidean space for S here. Now, initially you might start with the Dirac, but actually it's better not to start with the Dirac. You might want to put a distribution here. It doesn't have to be continuous with respect to the Lebesgue measure. You don't need to have a density, so then the solution here will be in the sense of distribution. Means you take a test function and you multiply here, and they're saying that the initial distribution is this one. All right. Now, this cost function here is not Lipschitz with respect to the measure mu. Most of our assumption here, we're talking about Lipschitz condition on mu, and here when you put 2, you see a quadratic in mu. Mu is the measure. So that creates some difficulties actually in terms of the classical assumptions that people ask. Now, another thing here is that when epsilon is between 0 and 1, so this term here is negative, so this is positive. So then if you do convexity assumptions, actually you don't have the classical convexity here because of the minus here. So that's the thing. So you might not have a convexity, you might not have a Lipschitz condition for this basic problem, but still we can solve it. And in the next slide, I will show you the solution. Now, why we can solve it? Well, is, this coefficient I'm putting here, 1/4 and epsilon, is to scale down so that the PDE becomes simpler. So this is because when you do functional duality for for a convex function L, you get the scaling in this way. So if you choose lambda as a scalar, so you get for X to be a scalar as well. Or if it's a vector, you just put the norm, L2 norm here, and you get the L2 norm in the other side here in P. And if I choose lambda to be half, if lambda is half, then I get here P. So this is what this property is the one that I'm using. And when I do that, I introduce the cost function, the optimal cost function, which usually people call it the value function for the optimal control problem, is just start at T instead of T naught, okay, of the previous problem. Now I change mu to be mu twin because so that you are not confused with the mu as a function of time instead of the mu that is fixed at the initial time. Okay. All right. So this value function, we can define what Eisenstein gradient for this value function, and we are interested in finding V and A. Okay. A is, and the terminal value function is given here from the terminal cost function, and the optimal control is given here, where V mu is the Eisenstein gradient. So we have the optimal control explicitly. Well, explicitly, we need to find this V, and V solve this equation. Now, you can start, if you want to solve this system, we propose this form because it was quadratic in mu. So we take the same shape as what appears in the cost function. So alpha is a function of time, a scalar function of time. Beta is another scalar function of time, and delta another scalar function of time. And then we take this and plug in this PDE, the PDE here above the Bellman equation, and then we get the ODE for alpha and beta. So it's pretty much easy in this case because now we can solve these ODEs. This is a backward ODE. Start at 1 means positive, and then you get a growing. You get alpha dot equal to 4 alpha square, which is positive. And actually, when you do a perturbation, you might get actually a finite time blow up, but it doesn't happen here because this is well defined. Same for epsilon. So if you take epsilon to be negative, for example, then there is a finite time blow up in this equation here because it is way plus here. Okay. So because of the backward structure, if you put negative epsilon, there is finite time blow up. Okay, in this simple equation, you get a finite time blow up. And it appears here because you get non-convexity structure that appears here. But still, we can solve this equation. So here I say semi-explicit because I didn't solve the ODE. Now in the next slide, I solve the ODE. And when I solve the ODE, I get this structure here. T is between T naught and T1. T1 is the terminal time. And you could see that there is no blow up here. You could see that there is no blow up in alpha, no blow up in beta either because epsilon is positive, right? So there is no blow up in alpha, no blow up in beta, and delta is just integration. When you integrate, you get this function here, the log here, which is well defined as well, positive, positive, so there is no issue here. So there is no singularity in this case, although it's not convex and although it's not Lipschitz. So which is interesting because it's very basic and it tells you maybe a way to go beyond the non-convexity and non-Lipschitz or type of things. Now, so we get alpha and beta, so we can plug it back, and when you plug back, you get this as the value function. So value function is given by the initial second moment, initial mean square, and initial mass. Well, this is normalized 1 because we took it as the mass to be 1. But for non-normalized mass, you can still solve it, and you might have this term to be not equal to 1. All right. So now the question is, can we extend this to 2 players? Because this was for 1 player. And this is what we have done. And that's where we 1 and player 2, and player I is optimizing this cost function where I change epsilon to be epsilon I so that I don't move that far. All right. So epsilon I. So there are two epsilons, epsilon 1 and epsilon 2. They are in this interval. And epsilon I here and epsilon I here. The Fokker-Planck is modified so that we put the choice of both players, A1 and A2. And when you change this to epsilon, actually the game is not a potential game. The previous one was a potential game because we had one player. It's a team problem. This one is not an exact potential game, but still we can solve it. And potential game is not a potential game in the sense of horizontal and Mondrian and Shapley. Okay. So again, we want to find a value function and we want to find the optimal control. We'll use the same techniques, same procedure, and the value function will solve now a system of Bellman equation, I and minus I, because we have, so if I is 1, the minus I will be 2, and then the Weizenstein gradients appear, and because of this term and this term are related to covariance if you put them together, and the mean square, the mean of the gradient square. Okay, so because of the square here, you get in non-linearity in mu. Linear in mu, and this one is non-linear in mu. So the red ones are the one that creates difficulties and the one that brings novelty in this problem. Now, we can solve it, but now the alpha beta becomes alpha I, beta I, and delta I, right? And the ODE becomes now coupled in alpha, coupled in beta, and talking about it. You can do a separation between the alphas and the betas. And the reason we can do it is because of orthogonality between the random variables that appear here and here. You could put the variance term together and the mean square separately. From to more general cost function. So in general, so we will be considering a function H terminal that is a function of the state, and the state here could be a vector or it could be just one dimension. Individual states together. It doesn't matter. So you can include correlations, for example, between player state, not just correlation through individual noise, but correlation between the state themselves. Okay, so that's represented by Y or S, and the mu T1 is the distribution at time T1, and this is the HI terminal. Time, state, distribution of state, and the action of all the players. So if you have n players, you have multiple players. AI is the control action of player I, and A is the vector of those AI functionals. And then you put the AI here. Now, so this is the system we started recently, and we are interested in finding, again, the value function means now equilibrium payoff, equilibrium cost of I, or optimal strategy. So means the equilibrium strategy, AI, right, of this problem. So here, compared to the previous problem, so here you have a system in I because you have multiple players. So you need to solve this system to get the Nash equilibrium. The solution of this will be Nash equilibrium of minifield type, sometimes called minifield type equilibrium. All right. The optimality equation write as follows. So V hat is the value function. It takes mu as a state now. So time, function of time, that belongs to this interval. And then mu as a state is a probability measure on S. S is R or RD here, okay? It's not that, it's an Euclidean space, this S here. Okay. There is no constraint or no restriction we are doing. So this is not limited to the torus because later on we'll do some applications and you will see too many interesting cases. this is the Laplacian term. Wilfred was doing. So where you can see that actually the log of mu appears is clearly seen here as a regularization term, the Laplacian HI as defined in the problem. So this is our Hamilton-Jacobi-Bellman equation to solve. But it is a system here because of the number of players, I. Now, you might want to say, okay, you want to study this. This is the number of players here goes to infinity. But the thing is, we didn't assume any symmetry in the problem. So if you want to study the limit of this, you need to bring out a special structure you want for those, because there is no assumption on symmetry we do in general manifold type game theory. And we don't do the assumptions mainly because of the applications. The symmetry assumption is really very restrictive, because once you do the symmetry assumption, usually people look at symmetric equilibria and symmetric equilibrium payoff. And actually in game theory, we know that asymmetric equilibria, some of the asymmetric equilibria might be actually good ones. So you're gonna throw them away and concentrate on symmetric equilibria and best symmetric equilibria also. So that's the reason why we keep the asymmetric structure. You might, so if you are interested not in the Bellman system, but in the master equation, because now it becomes master system, master systems of equations, then you get this problem here. The master, the master, the value function is a function of mu only. So there is no s in the value function here, but there is s here. So there is the reason is that when everything is smooth, u can be obtained as you take the Gato derivative in mu, you get u. In the case when everything is nice, means in the case where you could do the might want to start directly from here and existence of solution here, but then you get ui, which gives you the optimal control, which is true. It gives you the state feedback strategy, but u hat is not the value function. That's the issue. So this is not the value function in the mean-field type game problem, because the value function is this one here. So that's the equilibrium payoff, and not the second system here. Although the second might be interesting in terms of optimal control. You might get the optimal control here, but you don't get the value function here. All right. So in the particular case where the state is discrete set, then mu will be just a vector. Then you might relate this to the derivative of the value function and connect to the adjoint principle. Now let's look at solvability of this system, of both systems in the linear quadratic. Be one dimension, and the terminal cost is given a variance of s at time t1, weighted by a coefficient. Okay, this is positive coefficient, a scalar positive, and then the s bar is the average of s, and then we get s bar square here, so that is quadratic, and this is another positive. It depends on a factor that is a switching process, but so okay, it's a real varied function. Same for the coefficient here. This one does not need to be positive, but this one to be positive, and S bar here. So it's quadratic because variance is also quadratic, and the running cost as the same shape, variance, and then mean square, and variance of the control appears, because if you want to do risk-aware control, then you want to take control actions that have less variances, means as deterministic as possible. This is risk-aware control, and the mean square of the control action here. Now we add also covariance between the control and the state, which makes sense actually, because the control, the state, the relations between those. It's or with it together with the term here. And correlation between the control actions of the players as well. Covariance between the control action of the player. So this is our cost function, running cost. Now we need to integrate this cost function and add the terminal cost, and we want to minimize this, subject to the state dynamics. And the state dynamics is linear in the state, linear in the average state, linear in the control action of all the agents here, and average control action of all the agents. All right. Same for the diffusion term and same for the jump term. You could extend to other models. So this is about Poisson jumps. This is about diffusion coefficients. This is about drift coefficients. So when you consider this problem, actually in the one-dimension case, and we have extended some of the work to vector case and matrix case and so on. For this setup, you can solve it somehow semi-explicitly. Means if you can solve the ODEs, then the problem is solved. So that's why we call it semi-explicit. Now, the solvability of the ODE might require some extra conditions about positivity, about integrability, and so on. And this was known in the risk-free, mean-field-free case in the 25, and then a couple of other authors who extend to differential games, as we know. But the solution they obtain actually are different because the strategies that are used are different. So if you have open loop strategies, you get different solutions than if you have state feedback strategies. And here we are adopting state feedback strategies because we are using Hamilton-Jacobi-Bellman equation. But we could use maximum principle and we get different solutions from the solution obtained in state feedback. So that's the main issue with game theory. If you move from one player to two players, the solution, the strategy set you adopt gives you different so that makes people say, okay, I work on this space or that space, but actually this space or that space brings you to different solutions. In as far as we know for linear quadratic two-player game. Now for state feedback, we have solved it, the linear quadratic setup, and there is a toolbox that we created in our website. Games, competitive games, which is extension of cooperation and competition together, and you will find there, so the solution explicit. So I like this framework, although it's linear quadratic. It can solve it's relax some of the assumptions that are used in the literature, and you can check the solution. That's the good thing about it. You know the solution, you run your numerics, and you check. Okay. But in the other methods, I have a nice numerics, but nobody can check. I mean, it's just nice, but I cannot check. So here, and where it's working, where it's not, where it's taking time, and so on. So this could be a starting point here, and then progressively, okay, how can I move far away from here to add non-quadratic functions? That's what we have done. So now we go to non-quadratic. All right. Example of non-quadratic is to put a quadratic in the state, but not in the cost. So this is what we call quadratic games. In the state, you are quadratic, and in the cost, you are quadratic games. And we could solve those class of games for switching problems, means discrete state. Now, second category is to put quadratic in the drift. So again, quadratic in the drift. Quadratic. So this is again another quadratic, but the noise here. So this time the noise has a Brownian and a jump term, and we could solve this one subject to some conditions on the coefficients. Now, third category of problems we could solve is to put trigonometric functions. So here you have cosine square, here you have cotangent square, cotangent of s minus s bar. So this is really nonlinear, non-quadratic. Cotangent in the drift, and the
Hamidou, sorry to interrupt. I just wanted to give you an update. You got about 10 minutes or so to go.
All right. So we could solve this class of problems that are nonlinear, non-quadratic, and you can find more details in this paper here that's going to appear sometime in July in the automatic control. So for this class of problems that are nonlinear, non-quadratic, you could again do the numerics because the solutions are explicit, and check if your numerics are working. All right. So I will jump into the polynomial. This is the polynomial case where still it's not a Lipschitz function, but still you can do something. And in this case, we are able to solve it. And here is the solution explicit, because I'm putting switching and so on, but you will find it in details. I want to explain more the COVID-19 application. So let me jump over the COVID-19 business. And if there are questions, we can discuss later on. All right. So the COVID-19 two main sectors. One is the pandemic itself, and the second is the economic. You have probably realized that actually these two branches are creating problems in the measures and so on. So the pandemic aspect is, in terms of modeling, we want to understand the spread. We need a mobility map. So it means that the game will be run on a graph, the graph of the mobility map. In that game, we need the location, we need the position of the player, we need the infection status of the player, we need the age of the player, the gender of the player, the not family size, but the number of players with whom is at home. And then pre-existing conditions, because these are important in terms of prevalence and severity of when it's coupled with COVID-19. And then we compute the probability of getting exposed based on, if you go to grocery stores or if you go to work, well, whenever you go outside, if there is if you get close to somebody who is infectious, then we compute the probability by if there is any events like coughing or sneezing, then you get exposed in that surface, in that area, and the probability will be proportional to the exposure of that area, because this will be added as constraint. Now, the decision for authorities is about lockdown or so. So this is related to the mobility map. Decisions for firms is about protecting at their work. So if it's essential work, moderate essential, or less essential, we categorize them in three parts. And then for individuals, the decisions are related to meeting rate, controlling your meeting rate, decide to move, to go out or not. So this type of decision is done by individual. Now, in terms of economics, of course, individuals might want to look at their consumption. So when am I interested in getting food? I need to go out in that case or so. For firms, what type of production should I switch to essential production or less essential or moderate or so? For authorities, it's about allocation of budget between these two categories: the pandemic to protect people, and the economics, because we have unemployment rate that's exploding now, so you want at some point to protect that side too. Okay, so that's the context. We want to do this country by country, because for each country there is a specific parameter. We want that to enter into the model. And here is a display of the propagation. We had a video on this. I don't want to play the video because of the internet connectivity. So this is the propagation right now up to yesterday, May 7, and some selected countries because it's ranked by a number of infected. So that's why you see only some. So these are just 15, but we run it for 200 of them now in the platform. All right. So the details about authorities' decision is here. For example, decision is about migration and budget. Objective you say just the number of that, and I will give you the details on the dynamics. Decision about firms are here, production and working hours for firms, and they want to maximize their profit, although they don't say that. Okay, and then individuals want to maximize. Well, they want to reduce the risk of being infected, and of course, they want to look at their economic losses. Now, I consider only basic cost function, basic payoff. So this is the benefit when you work. This is the benefit when you go outside and get food. This is the cost function. And from pandemic perspective, so you want to maximize S. S means you probability of not being infected. S is successible. You want to maximize S. There is a variance there. The physical distancing. So you want to be far away from places where people are infected. Okay, physical distancing from X. So there is a certain bowl, and you count the number of people in that bowl, and you don't want to be there. Okay, this is V square is the velocity of that person. This is 2D. V is 2D, so that's why there is a norm here. And the variance because you want a risk-aware movement. Now, this is the cost function for individual. We plug that. And for the dynamics, I take the location, time, infection status will be successful exposed, testing, and isolation at home, hotels, hospital. You might some of them are hospitalized or recover or death. So these are the states. It's discrete. Age is continuous variable from 0 to 124 years. Okay, years old. So that's for age, it's continuous variable. And C is for existing health conditions. So we put MT means mild condition and then diabetes and so on. So then we get, for state, you get this state dynamics here, and we have all the details, the probability of transition, and we run, you get, this is the ODE dynamics. It's more heavy, but we want to capture the testing structure in the dynamics. And here are the details of the variable we use. This is the Kolmogorov equation that we use, and you can find the derivation in the paper by Ben Susan, Geish, Philip Yam, and myself to appear. And now the key thing is the interaction term, which is the probability of a successful person to meet somebody who is infectious. Because if you are not meeting people who are infectious, you are fine. So you consider the infectious. And here, infectious means the person has the virus, but it was not tested, or is really sick, but not tested, or he was tested positive, or he was at home, positive at home, tested positive at home, tested positive at point of care, or tested positive and at hotel, because some of them went to hotel, and hospitalized. So these are the infectious states, and they appear here. You need to consider them. And for beta, we need to add some interaction term. And right now, we are just counting over a ball. So the L2 distance. And then we need to plug this into the data. I need to conclude, but very quickly. So here is data. And we take the data that is online. I will give you the details. And then that data goes into the parameter. It's data dependent, and then I control that, and then I make a decision, right? And the data is here at this website. It's a public data, and the optimization step is just L2 minimization. You do that, you get the coefficient lambda to be dependent on the data. So new data comes means this lambda parameter will change, and then you run this over the map. So we take all the countries. Well, the data set, you have more than this number, and then you couple it with OpenStreetMap so that you can capture some of them of local movement. And the economic data is at AMS website. All right, so then you get this type of thing here. This is the red bar, or local mobility for specific countries. So this is initial distribution. This is when you run after a certain number of time, and this is the mobility structure here. And I run it for, this is India. So for the India case, you see that for the model, and the circles are the data. So it captures what is going on. And this is for Russia. and it's you can capture what is going on in terms of death, in terms of recovered people, in terms of infected people, and in terms of active people. Active means you remove the death and so on. So it captures for each of those data that is available, so which is nice somehow. And this is for Spain. Okay, so the model can track the data. It's not about fitting curves. Here is the epidemiologic model that is capturing the data. You have to take if you have any questions.
Okay. All right. Did you? I didn't hear what you said. Have you? Is that it, Hamidou?
It's over. The okay. Last point I didn't mention was the optimal control, but it's okay.